it's a really fundamental question. Both Andre and Hawking, and I think that was part of their rivalry, really, were zooming in on this, in my view, most fundamental question of all, which is how do we relate? How does our existence relate to the structure of reality on a global scale, on a cosmic scale?
Welcome to Closer to Truth. I'm speaking with Thomas Hertog about his expansive, visionary, important new book on the origin of time, Stephen Hawking's Final Theory. Tom challenges conventional wisdom in cosmology, challenges what Closer to Truth has presented for 2 decades on the multiverse. I love it. I love the book, which does not mean, of course, that I believe it. Welcome, Tom. I look forward to digging in.
Thank you. Pleasure to be here.
Let's start up front with an overarching summary of the book on the origin of time. Your core issues, ideas, arguments, conclude very, very briefly, just to get an overview.
Okay. Well, so our starting point, the starting point that Stephen and I took was, well, it looks like our universe, down at the level of physics, is somehow designed. It's perfect fit for life. And so one naturally wonders, how did that come about? Is there a designer? Is there an eternal mathematical truth? Is there a multiverse? Or is there a different explanation? And so the hypothesis that we developed over the last 20 years is essentially a different explanation, a profoundly evolutionary explanation, and hence, of course, also the title of my work, On the Origin of Time, I can already disclose, is a variation of On the Origin of Species of Darwin's.
Okay, now you're dealing with the fine-tuning argument as the motivation for looking at the various alternatives, and I think you listed 4: some mathematical certainty in the universe, a multiverse, a designer, and then, of course, what you'll be presenting in quantum cosmology. So those 4, dealing with the fine-tuning argument, you talk about a top-down approach in quantum cosmology to the standard, which is now standard, the standard model of cosmology, the bottoms-up approach of the universe, multiverse.
Yes, that's a characteristic of our approach, as you say. Just like Darwin's explanation is not a prior explanation for how the tree of life should develop and should branch. It's an, if you wish, ex post facto explanation or a retrospective point of view. And indeed, what Hawking and I developed is a similar kind of reasoning, but down in the earliest phases of our cosmic evolution, of the early phase of our universe. We claim that if you look at that phase from a profoundly quantum viewpoint, you've got to take a top-down view, or what Stephen would call a top-down viewpoint. You've got to look at it retrospectively, retroactively, indeed. So the kind of explanation that we put forward is not what you would call a prior explanation, say. It didn't have to turn out like this. It is more an ex post facto reconstruction of how the laws of physics came about.
Okay, we're going to get into this in a great deal of detail, but let me first give a brief biography of you, which is very impressive. Thomas Hertog is an internationally renowned cosmologist who was for many years a close collaborator of the late Stephen Hawking. Tom received his doctorate from the University of Cambridge and is now professor of theoretical physics at the University of Leuven, where he studies the quantum nature of the Big Bang. Tom, in your book, you talk about 2 events which seem to me to be bookends of your long working with Stephen. You talked about when you first met Stephen, when he took you as a graduate student. He said something like, I want you to work with me on a quantum theory of the Big Bang to sort out the multiverse. You know, a small question for for a graduate student. And then the other bookend was a few weeks before he died. He said to you that, Tom, it's time for a new book, a final homework problem. So give us some color behind those two bookends of your
Okay.
extraordinary relationship.
Thank you. Yes, these were two remarkable, typically Hawkingian moments, I would say. One may wonder what was the worst one, right? um, the first one that you mentioned, so it's very clear that towards the end of the 90s, the multiverse was on cosmologists' mind, right? It was on Stephen's mind, it was on André Linde's mind, it was on, and it would soon be on string theorists' mind as well. Of course, I didn't quite know what to answer Stephen in that first conversation when he raised that issue, but what was striking, even back then, Hawking was always someone who was very much driven by these big questions in his research. I think his genius really was to translate these huge questions that we all ask into theoretical physics language. And the apparent design of the multiverse, of the universe, the paradoxes associated with the multiverse were clearly on top of his mind back then. And I sensed, even in our first conversations, that Stephen wasn't all that happy with multiverse thinking. But also, he couldn't quite see a way out. And that really became sort of it was the kind of question that would stay with us for all these years, really. And that Darwinian picture that I talked about, that fundamentally evolutionary picture that I briefly mentioned, is something which only crystallized towards the end of our collaboration. And that, of course, explains the other sentence that you quoted, that once that crystallized and once at that point Hawking was almost no longer able to communicate, but he realized this was a grand new cosmic vision that was crystallizing in our work. Of course, he thought it was important to write as broadly as possible about this. And so that's what this book is about. As you know very well, Hawking had this immediate connection between his technical research and his outreach activities.
Okay, we have lots to cover, but what I want to start with is what you call in the book Stephen's opening shot. And you quote him in his synthetic voice that Andre claims there are infinitely many universes. This is outrageous.
Right, and and that is even a polished version of what was actually said.
Well, look, I've known Andre since 1999. He was, in fact, on the very first Closer to Truth, as well as several others. And his claim, along with many others, Alan Guth, Lenny Susskind, and Steven Weinberg, is certainly outrageous. No argument there. The question is whether it is also true.
Yes.
And so, you know, I think when we're dealing with the universe, outrageousness, they don't have a monopoly on outrageousness. I think you're going to give us some outrageous ideas as well.
Oh, that is certainly true. Yes, Stephen was just setting the scene there, right? Um, no, but there's another question too. Whether it's correct or not, there's yet a different question,
Yeah.
which is whether it is testable and whether it is a proper scientific theory.
Yeah, and that's a complex subject, and it has that has a lot of controversy today. Whether that is an absolute test, whether Popper's falsification is an absolute boundary for what is science and what is not. That is a controversial question.
Right, but a minimal condition there is that your theory, whatever it is, should make unambiguous predictions for what we should observe. So it is not so much the issue with the multiverse, I would say, is not so much the obvious fact that we can't go and check out another universe. The issue really is does the theory hang together as a theory, as a physical theory, as a theory out of which you can extract, out of which you can compute unambiguous predictions for what we should observe, for what we in our universe should be seeing.
Thomas, let me give you a personal incident which was very formative in building Closer to Truth, because when I first met Andre, again in 1999 on the first Closer to Truth, there were some things about his numbers of multiverse which disturbed me. And this is part of the outrageous part, because he was giving lower limits through some calculations about the number of potential universes in the multiverse. And one of the numbers he gave at one point was 10 to the 10th to the 16th. Now that's a 10 multiplied by itself a number of times, and that number is 10 to the 16th, which is 10,000 trillion zeros. So it's not 10,000 trillion that's the number, it's that's the number of zeros to count the number of multiverses. And then he had a further one, which is 10 to the 10 to the 10 to the 7th. I won't even bother to explain that number. Now, on the size of the universe, this was my aha moment to what this means about the structure of reality. Because when I read that number, 10 to the 10th, and there was another one, 10 to the 10th to the 64th, which is an exponent of 10 to the number of universes, 10 to with 64 zeros. When I read it again on my own, I said, well, what are the units? There are no units to this. Is it meters? Is it kilometers? What are the units? And I calculated that. Is it Planck lengths, which is 10 to the minus 35th, or observable universes, which is a order of magnitude difference of 62, 62 orders of magnitude difference between a Planck blank and an observable universe. So I asked Andre, not on camera, but before, to help me understand this, and then he explained that the units don't matter. It doesn't matter whether it's the number of Planck lengths or the number of observable universes, because that's a minuscule rounding error. It's not even a rounding error. It's so small compared to these numbers. And that was to be an aha moment for how outrageous the number of universes are.
Yeah, okay. So we both agree it's outrageous. But what I admire about Andre's line of reasoning that led him to the multiverse, and it's the same thing I admire about Hawking. It's a really fundamental question. Both Andre and Hawking, and I think that was part of their rivalry, really, were zooming in on this, in my view, most fundamental question of all, which is, how do we relate? How does our existence relate to the structure of reality on a global scale, on a cosmic scale? It's a question which has been sort of confusing, I would say, since the scientific revolution. And it's really a testimony, I think, to their genius that they zoomed in on that question. Of course, with widely different views.
I think it's wonderful, because really they have the same objective, and I think we'll all agree that no matter what the solution is, it will be outrageous, and that's how you frame the book with Hawking's and your will be a no boundary single universe built on quantum cosmology, with Lindy's and others, Alan Guth, etc., a multiverse, which Lindy has called eternal chaotic inflation, melded now with string theory and the anthropic principle. So that's their explanatory model, very, very simply. And that, the difficulty understanding it is, I told you my experience with it, but one can get that. Quantum cosmology is going to be more of a challenge and more fun. That's why I loved your book, because it's very clear how it is after you begin to understand the remarkable structure of it. So we understand the explanatory power of the multiverse, and also its problems. So now let's look at the no boundary hypothesis, which was Stephen's great insight that he and you developed together. Give an overview, then I want to really dig down in the various categories that are part of understanding it, in terms of understanding black holes, light cones, the cosmic microwave background, and then come to the no boundary hypothesis. What I'd like to do is give an overarching summary of the no boundary hypothesis, and then let's go into each of the technical discoveries or analysis that give rise to it.
Yeah. So, but I think the transition and this is the late 90s, this is the situation of my first conversations with Hawking, the transition between the multiverse and that quantum cosmology approach, which I revived with Hawking around that time, it really sort of has to do with the paradoxes to do with the multiverse. And a key point there, I think, is that multiverse cosmology, no matter which variant, doesn't quite tell you in which of these universes we should be. And therefore, what kind of physics, what kind of laws, what kind of stuff we should be observing. So we have a technical term for this in cosmology. We call it a measure problem. And the reason, and it's called a measure problem, it's, you can sort of intuitively grasp it. It's to do with the fact that we don't have a good measure to weight the relative importance of different universes in this multiverse. And it was the motivation to resolve that measure problem that led us again into the quantum cosmology realm, so to speak. Because, of course, we know that quantum theory comes with natural measures, which are these wave functions of probabilities.
Yeah. Now, to be fair, the way they handle the measure problem as far as why we're in this universe is with the anthropic principle, which again is very controversial. Many people don't like that at all, but that seems to be having widespread acceptance, certainly over the last few decades.
No, I disagree with that. Because the minute you have two universes which are habitable, your anthropic principle is dead. If you have two distinct universes,
I want to think about it. I'm not sure why would it be dead if I only have to be in one of them. If there's another one, it doesn't bother me, right?
It does the moment you want to predict something. Suppose you have two habitable universes,
yeah.
you want to predict your next observation. You want to predict, suppose these two universes are equally habitable, but one has a light dark matter particle and the other one has a heavy dark matter particle.
Sure.
The light one you're going to find with the next particle accelerator. The heavy dark matter particle you're not going to find. In your universe, should you build the next accelerator? Do you predict that you will find a new particle or not? The anthropic principle does not provide an answer. The theory becomes ambiguous, and you end up predicting that we should be vacuum fluctuated brains in an otherwise empty universe.
Yeah, so look, there are a lot of principles that are kind of floating around here. One is like a Boltzmann brain, but one of the ideas is that in an infinite, which these numbers get, start to give you the thought that maybe it's an infinite number. In an infinite universe, anything that can happen, even super remotely, will happen and will happen an infinite number of times. So that's the nature of infinity, and that screws up all your calculations, which is the measure problem as you're articulating, which is absolutely right. I'm not sure there's a tight relationship between the ability to predict, which is a scientific question of what you can know, with an ontological question of what really exists.
I agree. Sure. I completely agree. I was zooming in on the predictive aspect, because if the predictions become ambiguous, if it depends on what you or I call an anthropic quality, if we differ on what we call anthropic, we will end up predicting different things. We will end up selecting a different universe. And that ambiguity cannot be settled, neither by observation, nor by rational argument, nor by... I agree with you that this does not mean, this in itself does not constitute an argument against the multiverse. It does constitute an argument against the multiverse as a proper physical cosmological theory. Because the least we should expect from a proper scientific framework is that we can make definite predictions.
Okay, and that also is controversial. I was agreeing 100% right up until the final conclusion, because it is a point of contention in the physics community whether purely theory-based predictions can be considered science when they are beyond the bounds of experimental or observational confirmation, because we can't use this to guarantee an ontological position. But your point, narrowly construed, is that it's not a scientific theory if it will make ambiguous predictions, and I think that's right.
I mean, I mean predictions for what we can observe. I was not talking about stuff we can't observe. It's as simple as predictions for what we can observe in the future in this universe.
Okay. Okay, look, I think we've set the foundation. I really want to understand now the no boundary hypothesis, in terms of what it is, and then what are the physical aspects of discoveries in quantum theory and black holes and all of the different aspects that contribute to its creation and confidence in its accuracy.
Great. Let's try.
Okay, good. I'm listening. I'm going to listen closely, right? and I'm prepared to be outraged.
Okay, so yeah, where should we start? Ooh la la.
Well, just the no boundary hypothesis that as you get back to that, run the movie in reverse, you don't get a point singularity.
Yeah, right. If you were to go back to the Big Bang all the way and you were blindly trusting Einstein's theory of relativity, then, as you say, you would run into a singularity where the theory breaks down and has nothing to say. In fact, strictly speaking, that singularity, that sort of state of total crumbling space and time and in infinite curvature, strictly speaking, that singularity lies outside the realm of Einstein's theory. So it kind of suggests it's not knowable. This, of course, was unacceptable to people like Hawking. And the obvious line of attack, and so now we're talking about late 70s, early 80s, was to say, well, surely quantum gravity becomes important early on in the history of the universe. And it's interesting that around the same time, late 70s, early 80s, Hawking was losing the ability to write equations. And I think this motivated him to devise a kind of way of thinking about the quantum realm of gravity, the quantum realm of space and time, which you could kind of visualize and manipulate operations in your head. And so the obvious inroad there was essentially Einstein's very geometric understanding of gravity. And so, in a sense, you could say that Hawking, with his no boundary proposal and his take on quantum gravity, pushed this Einsteinian thinking about curved spacetime further into a realm, into curved spaces which have no time direction, which are purely spatial forms like spheres and higher dimensional objects, wormholes and all that. So I think he sort of got the idea from working on black holes.
Because what he did with black holes, Roger Penrose, of course, which he won a Nobel Prize in 2020 for his predictions of black holes as a robust prediction of general relativity, were very well deserved and critical, showed that time changes, time ends in black holes. What you say Stephen did is he took the argument in black holes, which seemed to be very robust, and then applied that same time reversal to the expanding universe.
Right.
And that, to me, in understanding no boundary hypothesis, was the really critical concept, because you had this pretty much theoretical verification in black holes, which with data that has come much more recently has been confirmed quite accurately in a remarkable way. But Stephen used that idea for black holes to apply to the entire expanding universe. That was, to me, the remarkable innovation which led to that grounded the no boundary hypothesis.
Yeah, there are two levels, but it's true, of course, that I think, in fact, through his entire career, there was an interplay between insights in black holes, which Stephen would then apply to cosmology. In a sense, his real problem was the origin of the universe. And the reason was that he felt that this was sort of the why it really mattered, our research. It was about our own cosmic origins. The singularity of the Big Bang is in our past. It tells us something about us, about our deepest origins. But black holes were the perfect lab for Hawking. And so, as you say, he did this first in the 60s. That's what you're describing. Penrose's black hole singularity theorem say time ends in black holes. Hawking's singularity theorem says time has an origin in the Big Bang. But he did this a second time, and that's when the no boundary proposal comes in. He did this the second time, late 70s. By that time, Hawking had discovered that quantum effects make black holes radiate.
Yes, very famous.
And in the late 70s, he had devised a kind of calculation of that Hawking radiation process, which did not involve time. It was a purely Euclidean spatial calculation. And so he had already devised thinking about quantum gravity in terms of purely spatial curved geometries without a time dimension. And this left a very strong impression on Hawking. He concluded that, wait a minute, we can use these geometric techniques of Einstein, but without a time direction, to somehow unlock the quantum realm of gravity. And so he reproduced the phenomenon of Hawking radiation from a purely spatial black hole, a version of a black hole geometry. These look, frankly, these two look just like cigars, where the tip of the cigar is the horizon of the black hole. And so then, because this left such an impression on him, this worked so well for black holes, the obvious thing to think was, wait a minute, if those purely spatial geometries tell us something about the quantum realm of gravity and space and time, surely we can do the same for the Big Bang. And that's how his no boundary construction comes about. It's essentially an idea where if you trace back the expansion of the universe, that in some sense, when you go far enough back, you lose the time dimension. The normal time evolution sort of evaporates and turns, this was the model, turns into a space dimension. Why a space dimension? Because it worked for a black hole, and secondly, because if you had all space dimensions, you know what you can do. If you only have space dimensions, you can close all dimensions like a sphere, like a little bit like the south pole of the Earth.
It's a supremely original idea that's very powerful that Stephen developed with Jim Hartle as well as part of the process back then. We've spoken to Jim in the past. It's a startling idea that time changes to space, and therefore at that beginning, when you first hear about that seems so counterintuitive. But when you understand that what's happening in black holes, that suddenly gives you a theoretical foundation how this could be real.
Yes, but I can assure you it is counterintuitive. Sure. But indeed, it's a supremely ingenious solution to what seemed like an insurmountable problem. How can you get rid of time in a controlled fashion well, here's a way to do it. And that was essentially, I would say, the highlight of Brief History of Time, right? This new
Yes.
theory.
Let's talk a little bit about the cosmic microwave background, because this is used as maybe the primary data. There's others as well in terms of the standard model of cosmology. It validates the multiverse in terms of their thinking. You describe it really well. I mean, we've talked about that a lot on Closer to Truth, but you describe it really well in the book, particularly in terms of the not what you call not just a surprisingly uniformity across the sky, but this is absolutely mysterious. You say, because if you run it back, the universe has really, as you put it, several million independent cosmic horizon-sized domains, because there was not enough time in the early universe for the things to communicate together. And so to see the uniformity, which seems okay, well, uniformity seems normal, but when you recognize that all these independent domains that never had a chance to communicate, that uniformity becomes mysterious.
Oh yeah, definitely. Yes, yes. It is perhaps in the hot Big Bang. I sometimes say that the Big Bang model, the Big Bang theory, without inflation, the old Big Bang theory, is both the cornerstone and the Achilles heel of modern cosmology. It's the cornerstone because, as you say, we have the CMB, we have the background radiation, it all hangs together. It's the Achilles heel for reasons that you just evoke. How this uniformity is utterly mysterious. But of course, inflation solves that problem. Inflation makes it a lot less mysterious,
Yes.
right? Because it connects our entire observable universe at earlier times. And I must say that you might wonder, in Stephen's no-boundary construction, in Stephen's no-boundary hypothesis, what kind of universe can you get out? Because after all, he's doing something really drastic. He's sort of changing time gradually into a space dimension. This doesn't work in all sorts of universes. In fact, it works only in universes where the classical space time, where the classical fabric of space time emerges through a phase of inflation, essentially. So that no boundary construction, that no boundary idea, and the idea of inflation, and you will say, and the idea of the multiverse, they're a triangle of ideas that are closely related.
I like what you talk about as a duality in physics, which I hadn't heard that term used in quite that way, where you have the laws of evolution, not biological evolution, but how things transit from one to another, which are classical Lagrangian and Hamiltonians and Schrodinger's equation, and which everybody talks about, and the initial boundary conditions. And so those two have to articulate together, and that a theory to work must deal with both of those. And that's one of the reasons that the no boundary hypothesis has more credence, because it deals obviously strongly with the initial conditions.
Yeah, you're repeating Stephen's mantra, right? But indeed, he was very keen on that. Of course, normally, in all other problems in physics, we don't regard boundary conditions as part of the laws. We regard
Right.
it as a choice, and that's okay. In fact, that's perfect. But then there is this problem of the origin of time, of the ultimate boundary condition, and then related to what we have been discussing, you can do two things really. You can either say, well, even the Big Bang, even the origin of time, is not quite a boundary condition. There is yet a bigger system, and that is the multiverse idea, or the idea that there is a phase of the universe before the Big Bang. And so what almost ontologically differentiates the multiverse from the no boundary idea is to say, no, we're going to do something different. we're going to devise a law for this ultimate boundary condition, and that's going to be part of physics. It's going to be almost like an extension of physics. So they're two radically different hypotheses.
Yeah. You quote Stephen when he gave a talk at the Vatican, and I'll read it to you, and then you'll give us some color, where he said, there ought to be something very special about the boundary conditions of the universe, which I think everybody would agree with, especially if you believe there's a creator designer. But then he added, but what could be more special than the origin of the universe? What could be a more special boundary condition than there is no boundary?
Right. Right.
So this is,
Yeah. Yes. Yes.
what was the reaction at the Vatican when he said that?
Well, he said that after the Pope, a few days before that, had essentially told the congregation of scientists that the origin of the universe is beyond physics. So you could almost read Stephen's talk then as a kind of a response to the Pope's elocution. But still, I think back at the time that was the Hawking of the early 80s talking, right? At I would say the zenith of his confidence in physical theory, the Hawking of A Brief History of Time, the Hawking who believed that he was on to some final theory of everything, an ultimate grounding, an ultimate truth, which included the idea of a theory of conditions, but it was there, his theory of initial conditions had a sort of, how do you say that, almost transcendental existence. It sort of existed above and beyond the universe, and it dictated how and why the universe could be, the physical universe could be created. So it was almost like a Platonic truth, which he then, in A Brief History of Time, famously related to the mind of God. That is not the Hawking that I've known.
Let me just give you some quick observations, and give me a quick reaction to each, because we have a lot to cover, and just there are so many different aspects to this that I just find absolutely fascinating. You liken Andre Lindy's chaotic eternal inflation to Fred Hoyle's famous steady state hypothesis, which, and when you do that, you're certainly not saying that as a compliment.
Well, look, of course, I respect Andre a lot.
Of course,
but he's a bit a bad character in my book. Yes, of course. I mean,
and I'm sure he loves it.
I had to write it as a detective story, right? Yeah. Because all good books are detective stories.
Yeah. Yeah. So, and so, how does Andre's chaotic eternal inflation equate to Fred Hoyle's steady state? What's the nexus?
If you were to look at the multiverse at a truly global scale, as if you're outside it, and you were to look at it, then in fact it would be some sort of steady state in which new universes pop out consistently, and various different kinds of universes would be constantly created in certain proportions, while the big space would keep on inflating. And so it's a little bit like the picture of Hoyle, where at some point Hoyle recognized that galaxies are moving away from each other,
and you have to explain.
But there are constantly new galaxies being created, leading to, globally, a steady state.
String theory, as it began to develop coterminous with this developmental thinking, has, at least in the common conventional wisdom, has given more encouragement to the multiverse, because the string theory, with its multiple structures, so-called 10 to the 500th, whether that's right or not, it doesn't matter. But there seems to be an interplay that string theory and the multiverse seem to work together in various ways. So string theory is controversial, but if it is, it certainly has a lot of adherents. And if that's true, it would seem to articulate well with the multiverse theory.
Yes, if that's true, yes. Um, it certainly, string theory to me certainly lends credence to the idea um, that mathematically there could be a wild range of different kinds of universes, differing even in their laws of physics. I think initially in the 90s, people like Andre had in mind, okay, a multiverse, but when string theory came along, the multiverse became a true patchwork of all kinds of different universes. Yeah. So the scope of variety of the effective laws of physics became, with string theory, indeed huge, I would say. Sure.
Yeah. Again, that doesn't confirm it's accurate. Both multiverse and string theory are both controversial in a way. String theory even more so, of course. Um,
Yeah, so I think what string theory added to that game was really what we were talking earlier about. It sort of suggested that the multiverse could be a truly alternative explanation for that design question.
Yeah, and the design question is always hanging out there as the alternative, which in popular belief is of course very strong. But in the scientific circles, one needs to deal with that, and it seems like, and correct me if I'm wrong, there are only three broad categories of dealing with it. Originally, there were two. The idea of chance and necessity seemed to be the only alternative to a cosmic designer. Necessity meaning there is some mathematical theory, equation that when you see it, you will have to recognize that it had to be this way, and therefore there's no alternative. That is the holy grail of physics broadly. I mean, from Einstein to everybody. But over the last few decades, that seems more and more elusive and more impossible. And therefore, the chance hypothesis is the multiverse, that you have an infinite number or virtually an infinite number. So anything that can happen will happen. Then you have to use the anthropic principle to say, where are you? But you can only know where you are by being a sentient observer. So that solves it. And then, of course, what Stephen and you have brought in is a third way which people had not thought of before. Is that?
Oh, yeah. I completely agree with that. And I don't know how you feel about it, but I sort of feel that the third way is a little bit of a middle ground between these two extremes that we had before. A unique, mathematically determined universe and a situation in which everything becomes possible.
I hadn't thought of it, but you're right. I can, first approximation that's a nice way to put it. I'll give it some more thought. I'm not sure I'm going to continue to think that way, but I like that. I like that a lot. Now, important to your arguments for the no boundary hypothesis versus the multiverse is a critique of anthropic reasoning, because anthropic reasoning absolutely is essential in the multiverse, and you don't need it at all in the no boundary hypothesis. So that becomes a target that you're shooting at. One of the claimed verifications of anthropic reasoning is what Steven Weinberg did very, very early on, used anthropic reasoning to come up with an estimate of the cosmological constant, which many people thought was a verification. I'm not sure Stephen even thought that himself, but it was certainly an interesting observation.
Stephen certainly flirted with the anthropic principle many times, going back to a brief history of time. So I think he sat on the fence on it for quite a bit. And then, of course, I don't deny that there are some basic qualitative features like Weinberg's prediction that go together with us being here. But the real critique starts when you try to make other predictions or make better predictions because the anthropic principle builds in the idea that we, defined in some way, are typical. And let's contrast this with Darwin. Did Darwin assume that we have a tree of life on Earth in which this is a typical Homo sapiens branch? I don't think he did. And moreover, Darwin didn't need a zillion other planets to figure out biological evolution on this planet. It's a fundamentally different approach not to assume typicality. And that's, I think, where the real differences begin to enter between quantum cosmology and the multiverse.
So, Thomas, let's now talk about how quantum cosmology works and how the superpositions of the histories of the universe can lead to where we are today. A remarkable idea that we all recognize is outrageous. The question is, let's understand how it works, because something has to explain where we are.
Yeah, so we have all these histories in quantum cosmology, all these different universes, just like we had many histories of particles in the usual quantum theory. Now the situation seems worse. We have all these different universes. So it's a kind of quantum version of the multiverse, if you wish. But quantum theory comes with a selection principle of its own, namely the act of observation. That was Everett's grand idea. And it also works somewhat retrospectively or retroactively. That's what John Wheeler developed. And we apply it here in cosmology. The act of observation, the final state, if you wish, selects a small subset of histories of the universe that are consistent with what is being observed.
So this is, of course, the primary point and the pinnacle of outrageousness to appreciate that from that no boundary condition to today, there were, I don't know if that's the right term, there were or are, but there were all these histories that, because we are where we are now, we are in a sense selecting one of those vastly innumerable histories. We are selecting it now by observing where we are. Now, to simple me, that sounds like backward causation.
Yeah, and I think it's pretty right. It's pretty correct. There's a retroactive element in all this. A history or a universe, if you wish, or if we do this in the full picture, even the laws of physics are not what they are a priori, but only ex post facto. Now, in the last few minutes, we are kind of mixing a little bit the traditional sort of causal deterministic bottom-up reasoning forward in time, and then we're sort of bringing in this retro-causal element, right? And so this was very confusing. In fact, the kind of discussion we're having now, it was the kind of discussion I was having with Stephen in 2005. Because I would complain, Stephen would say, it's all retro-causality. We have to think about it, what he called from the top down. We have to forget the original no boundary idea, that it is like the creation of the causal creation of some sort of universe. And for years, our argument went back and forward, because I told him, look, this is like putting in the answer. It's weird. I didn't use the word outrageous, I think. But then, from 2012 onwards, holography came around. And so we started to develop a holographic formulation of the no boundary idea. And by that I mean, well, it's a long story.
Define holography so we can all understand that, where three-dimensional information is encoded in 2 dimensions.
Yeah, so holography, like a hologram, is some sort of thinking, some sort of model in theoretical physics where there's an extra dimension that sort of pops out.
Yeah.
In general terms, right? We've heard a lot about the ADS-CFT correspondency that Madlasena discovered. Holography also has its roots go back to black hole physics, where all the information, all there is to know about a black hole seems to be encoded on the surface, meaning that the interior of the black hole is in a sense an emergent dimension. So holography has been the talk of the town in theoretical physics for years now, although for many years it didn't really sort of penetrate cosmology. Holography was done, say, for black holes and for in the highly mathematical universes of string theorists, but not quite in the cosmological context. But then, so yeah, almost 10 years ago, it began to dawn upon us that Stephen's old no boundary theory, no boundary proposal, this whole idea that time turns into a space dimension, emerges from a holographic thinking about the universe in which you kind of represent reality or our observed universe in a super abstract way, in a holographic way, and in which the past time dimension is the dimension that pops out. So holography in a cosmological context, the extra dimension is not the space dimension, it's the dimension of time. And of course, that was the dimension that has been causing us problems for decades in cosmology.
Yeah, a remarkable idea. And Carla, I love how all the ideas that are emerging from black holes in terms of time, holography, are applied to the universe. I mean, that grounds what your approach to quantum cosmology. It grounds it on very fundamental physics that we're pretty confident is correct, and that gives great credence to your outrageous idea.
Right. So the outrageous part, even to us now, was that when we realized that Stephen's old theory emerges from this holographic way of thinking, it emerges in this retro-causal manner. That was the strange thing. It's sort of, holography sort of anchors the laws on our observational situation within this universe, and it works backwards in time. And the further you go backwards in time, the more of a fuzzy view you take on that holographic description of our reality. And if you go all the way back to the Big Bang, it is almost like you're running out of bits, you're running out of information on your hologram. And so Stephen's no boundary idea in the modern language of holography is literally that you've run out of bits. You've run out of information, and there you go. You lose your time dimension. It's a mind-boggling idea.
Yeah, but when you phrase it that way and you build on that, it's mind-boggling. It continues to be mind-boggling, but it has a rationale to it that without it, it just is just sort of a naked outrageousness. Now it's an outrageousness that you don't lose your sense of outrageousness, but you see it grounded in hardcore physics, and to me that's very exciting. Still may not be right, but it is exciting.
Thank you. Yeah, no, it's grounded as best as we can, and the surprise is that it builds in this top-down view, which we had been debating for so many years, and which we sometimes felt, and this was that was the criticism also in the early days of top-down cosmology from people like David Gross, right? He would say, hey, wait a minute, you put in the answer that everyone else is trying to derive by working retro-causal, right? And now we can say to David, look, holography just works that way. And we have to develop this. This is a grand new hypothesis, which is a bit of ontological readjustment, because with that, or what's happening now at the Big Bang, it's not just the origin of time, you also lose any notion of laws. And that's where my Darwinian turn comes about, right? The laws of physics from that holographic viewpoint don't reach further back. And that is the crucial sort of Darwinian idea.
Does the multi-world interpretation, the ever-written approach, which is again controversial in physics to be sure, but has a number of adherents that supposedly take the Schrodinger equation literally, so there's no collapse of the wave function, but every whatever time period the universe branches into these innumerable branches. Does that theory help? Is that a supporting theory to the no boundary hypothesis?
It's a good question. In the old days, when people like Jim, Hartle, and Stephen were doing no boundary cosmology, I'm pretty sure they were building on Everett's legacy. And to some extent, this was kind of necessary, right? How are you going to do quantum cosmology without you can't do the collapse of the wave function because you don't have an external observer. So to me, Everett indeed paved the way for quantum cosmology. But now, in this holographic way of thinking, it seems to me there's more going on.
And does the holographic approach obviate the need for the multi-world interpretation?
Well, that is the crux of our theory, of course, that the other universes, they just disappeared from our equations. The hologram doesn't encode more than one universe. It encodes just ours, and that's sort of the heart of our... It is almost... But what does this mean? So now we go back to your previous question. First I thought, okay, the multiverse is gone. But I think, in fact, there is a more precise interpretation of this, a more subtle interpretation, which is more like maybe the other universes are out there, but quantum cosmology is somehow telling us that we can't know anything about them, that they don't interfere or they don't affect the way we do physics and the way we derive predictions in our universe. In fact, it is very much like how you think of Darwinian evolution. Of course, there are a zillion other planets around, and they may or may not have life, but it doesn't affect how we do biology on this planet. So we don't use other universes in our derivation, in our predictive framework for cosmology. That is the difference. It's almost as if quantum cosmology is saying that there is is incorporating, and quantum theory is very good at telling us what we can know and also telling us what we can't know. It's almost as if the theory is telling us there's a limit to what we can know.
I mean, that is coherent. That makes sense. Again, the sense of outrageousness continues to diminish. In terms of the physics, it doesn't disappear, but it does diminish. But still, the past is contingent on the present. Is that simple statement correct?
Yes.
The past is contingent on the present.
Yes.
And go ahead. Can you distinguish what I just said? The past is contingent on the present. Would you say yes? From backwards causation. Are they synonymous, or is backwards causation? Backwards causation is sort of a simple statement that's non-quantum. So is that the distinction between the two?
Exactly. That's a little bit the subtlety and the distinction. Backwards causation, I would interpret that term as we can send signals back in time.
Yeah.
That's not what this is about. That's not what this is about. The retrocausal aspect of our theory enters only down at the quantum level, and it is really a way of thinking about the sort of act of observation in quantum cosmology, namely that without a final observation down at the quantum level, you have a wave function and no definite past histories. But that observation is always done down at the quantum level. It can be done by one single lone photon or an interaction between fields. So we are not saying that human observations today fix the entire history of the universe. No, the acts of observation that selected the laws of physics have been done by the interactions in the earliest stages of our universe when these laws crystallized out of a zoo, out of a wide horizon of possibilities. So it's not quite traveling or sending signals back in time. No, no, no.
Okay, that is coherent. Now, you claim, again, that the anthropic principle is rendered obsolete by the no-boundary quantum cosmology, and I can understand how that's the case. What I'm wondering, though, is it seems like when you have the past contingent on the present, that in some sense, the anthropic principle is returning in stealth mode, because we have to have where we are in the present to define the past. So that sounds like it's also a kind of a backfill of the past based on the present. And so it seems like it's something between the anthropic principle and circular reasoning to make this happen.
I think the key point there is that we treat all different data and elements and facets of our universe on equal footing. The anthropic principle always makes a separation between certain data that are called anthropic and relevant and which are typical aspects of our universe, and other data. We treat all features of our universe on equal footing, and in that sense there's no anthropic preference or whatever. But I agree, the final condition, very much in this holographic formulation, the final configuration enters very much in our reasoning. Just like, once again, in Darwinian evolution, Darwin looks around, looks at all possible fossils, doesn't prioritize, doesn't privilege Homo sapiens. No, he looks at all possible fossils and reconstruct the tree of life. In the same way, Stephen and I reconstruct the tree of laws, and you can only do so with a genuine theory of the origin.
You have this concept of evolution, the Darwinian analogy, and in quantum theory. It makes no sense to ask where that came from, right? Because you have.
I knew you would.
But I mean, that's part of your initial condition, in which you have to say is a brute fact that that's the way the universe is.
I agree. Yes, right. I think this sort of fundamental evolutionary understanding, where if we go back to the Big Bang, we even lose the notion of laws of physics. It sort of implies, and I think this is where you're getting at, it sort of implies that we don't really have a foundation. You see, the two other attempts that you were at sort of tackling the cosmic design question, the multiverse and the unique mathematical theory, both of them could be thought of as a foundation for all the rest.
Yes.
The mathematical theory is clearly one, and the multiverse, governed by some overarching meta laws, is also a sort of a foundation. And you're absolutely right that, and this is again probably some sort of ontological point, we don't have a foundation. In fact, we sort of, our hypothesis, certainly the holographic formulation of it, in which the history and the laws and everything in the past are fundamentally emergent. Our hypothesis builds in a certain finitude, I would say, which is probably, from an epistemic viewpoint, the key difference between the two other approaches. Yes.
Yeah,
Yeah.
I think that's a very important epistemological point. Thomas, I'd like to go back to your favorite target in the book, Andre Linde. You mentioned in the book that when you saw Andre, 20 years later or something, Andre was recognizing the importance of quantum cosmology, and as his theory has developed, I think that's right. And you seemed a little maybe surprised by that or encouraged by that. I'm not sure what the right way is. What I found surprising early on with Andre is something a little different, in that he has, in terms of the foundations of where we're talking about, foundations of the multiverse or the mathematical laws or quantum cosmology, he has a different kind of view, that he puts consciousness into the equation. And he tells a wonderful story of whether it was an early book or a manuscript, that the publisher told Andre to take out a reference to consciousness at the end, because if he did, the scientific community wouldn't respect it. And he told me his answer was that if he takes it out, he won't be able to respect himself.
Oh yeah. Good. Excellent. I can completely understand his answer. Yeah. So as I was saying in the beginning, I really admire Linde and Hawking for putting our existence into cosmology. It's been an enigma since the beginning. Physics and biology, in the ontological sense, have a schism in between them, and sort of, to me, Hawking and Linde were pioneers in trying to bridge these two.
Yeah, I absolutely agree, and I think that's why your book is so important, because it highlights that you have a personal parochial position to defend, and I respect that. But you present these as two critical theories for addressing, our existence, incredible as it is when you really think about it.
Right.
So a wonderful book. I really appreciate it. I want to conclude, Thomas, with just some quick observations about black holes that have been recently in the news, and just to get a very short reflection on three specific questions. One is, what is Hawking radiation in reality? Because there have been critiques that have said that Hawking himself, in his books, mischaracterized what Hawking radiation is, as at the event horizon, when you have the spontaneous emergence of a particle and an antiparticle, that the event horizon, the one that's inside, will go one way, and the one that's outside goes another way, which is a very simple way to understand it. So therefore, you can see the radiation going away at that. But that's been criticized as that's not how it happens. It happens some other way. It happens more distant. What is the truth? Did Stephen mislead us about what Hawking radiation really is?
No, I wouldn't say so. But it's true that there are wildly different pictures or understandings or even calculations that lead all to the same net Hawking radiation effect. As I mentioned, you can even calculate Hawking radiation without any notion of time. That leads yet to another picture.
So what you're saying is that Hawking radiation is obviously real, but actually how it's really working, there's some uncertainty.
Yeah.
Because everybody seems to be certain about how it works, is they just differ.
Yes, certain. In fact, it's a striking fact. There are so many different calculations leading to the same net effect. So what is the best way of thinking about Hawking radiation? That question has yet to be settled, perhaps. Yeah.
Okay, good. I mean, I'm happy with that. Second was, recently, researchers have said that black holes will eventually destroy all quantum states. That they say new calculations show that the event horizon around black holes will decohere quantum possibilities, even those that are far away at the other end of the universe. I mean, that seems to make no sense to me, but I'm reading it.
Yes, I'm reading it too. Well, that is to me rather wild speculation. I'm
Okay.
I'm not so much on board with the.
Okay, good, good. I mean, I'm going to trust. I'm going along on your trail. I'm kind of. And the final one is that there may be some primordial black holes that were pre-Big Bang from previous cycles. Now that would seem to contradict the no boundary hypothesis, if
That
that's
would be
true.
impossible in the no boundary cosmology.
Yeah, and so you obviously don't go along with that possibility.
Right, right. But of course, that touches on an important point, which we have not developed. We have these grand hypotheses on the Big Bang, but we have really scant fossil evidence of these earliest phases. And so I think what should be done now is to develop those hypotheses to an extent that we can actually begin to test those. For instance, I see the 21st century as the century in which we hopefully will get some clues from observations about these earliest fractions of evolution, sort of gathering fossils.
Tom, I think your book is a major contribution to current thinking. It brings to popular and broad audiences an approach that I think is critical to understand, right or wrong. It is opening these questions to fundamental analysis and hopefully experiment or observation or more theoretical work. So I certainly highly recommend it to everyone as a critical book for the 21st century.
Thank you so much.
Viewers can watch hundreds of videos on cosmology, quantum physics, and quantum cosmology on the Closer to Truth website and YouTube channel. You can watch the leading physicists. In fact, I'm going to give you a list of the physicists that are mentioned in Tom's book, the characters of his main play that people can see videos on from all of these people. And every one of these are in Tom's book. And I'm going to list them as I found them in Tom's book in chronological order in Tom's book. Henri Linde was obviously first. Alan Guth, Roger Penrose, George Ellis, Paul Steinhardt, Andreas Albrecht, Lenny Susskind, Stephen Weinberg, David Gross, Ed Witten, Juan Maldacena, Murray Gell-Mann, Kip Thorne, Paul Davies, Martin Rees, Bernard Carr, Robert Digraph, George Smoot, Max Tegmark, Alex Valenkin, Don Page. I may have missed some, but all of those people are in Tom's book and on the Closer to Truth website and YouTube channel. Tom, it's been a great pleasure. I love the book. Hope everybody can read it, certainly Closer to Truth audiences. Thanks, everyone, for watching.
Thank you so much, Robert. Yeah, wonderful. These are all my characters, indeed.
Thank you for watching. If you like this video, please like and comment below. You can support Closer to Truth by subscribing.